Hello everyone, I am Kerem Erdal. Welcome to my YouTube channel. Today I am going to introduce you topic Burrow-Wheeler transform. Firstly, I want to briefly introduce this topic and why it is useful. It is mostly useful for compression by reordering the text, and it is used in some compression techniques such as bzip2. It was invented by Michael Burrows and David Wheeler in 1994. And it can also be used efficiently for pattern matching problems by using it along with Ferragina-Mancini index. So, I want to introduce how we can do Burrow-Wheeler transform by illustrating it with the example of the string banana, and we will try to obtain the Burrow-Wheeler transform of banana. In the first step, we append a character smaller than all the alphabetical characters to the end of the input string. We can choose $sign as a character smaller than all the alphabetical characters, so we can append it to the right of the string and it would become banana dollar. In the step 2, we generate all the rotations of the new string obtained, which is banana dollar. Now I will explain how we obtained these rotations. Firstly, we wrote banana dollar in the first row, and then we rotated the string to the left. For example, this $sign became a one character left shifted, and A is also shifted to the left, N is also shifted, A is also shifted, N is also shifted, A is also shifted, and B is shifted to the left. And since it is the blank space, it is transformed into the end column. And by doing this left transform at each row, we obtain 7 different rotations of banana dollar string, and it is equal to the length of that string. In the step 2, we sort all these generated rotations in lexicographical order. Since $sign is smaller than all the alphabetical characters, the string starting with $sign is in the initial row, and then the strings starting with A come, and $A is smaller than AN, so it came firstly, and $A is smaller than AN, so it is before the following row, and this logic continues up until the last row, so these are lexicographically sorted. So how can we obtain the Burrow-Wheeler transform of banana dollar? When we take the last letters in each row, we can construct the Burrow-Wheeler transform easily. So these are already in the sorted manner. Thus, if we take the characters in the last column, we can directly obtain the Burrow-Wheeler transform, which is ANN B $AA. So we successfully found the Burrow-Wheeler transform of banana dollar by using the appropriate steps. So mostly L to F mapping property of Burrow-Wheeler transform is useful in pattern matching problems and also in some other issues such as compression. What is it? It refers that end occurrence of a character in last column correspond to end occurrence of same character in the first column. So I want to illustrate it. For example, this A is the first A in the last column, so it corresponds to first A in the initial column. The second A in the last column is same one with the second A in the first column, and the third A in the last column is the same with the third A in the first column, and we can also observe it by looking to the patterns. For example, it is the A coming before $sign, and also the matched A is also the A coming from the $sign, and same logic can also be used to check if it is correct, and it always holds. Now I will explain how to find the actual string using L to F mapping. For example, if we just have the last column given to us, we can already obtain the initial column, as these are the lexicographical order of 3A, 1B, 2N, and $sign. So we can obtain this first column directly when just the last column is given. So how can we obtain the actual string by using the first and last columns? We firstly start from the end of the string, which is dollar sign. And what is the character before dollar sign? It is A, because it also indicates the rotation of this string. So banana dollar, and dollar is the sign coming after A. So the character before dollar is A. So we can watch this pattern recursively by using also L to F mapping. And I will illustrate how to obtain it. The character coming from dollar is A, and this A is the first A in the last column, and it corresponds to first A in the first column. And the character coming for A is N in the same row, and first N corresponds to first N in the first column, and the character coming before it is A, and it is the second A in the last column, so it corresponds to second A in first column, and character coming before it is N, and it corresponds to second N in the first column, and character coming before it is A, and we can watch the same pattern once more. The character coming before A is B, and there is single B in the first column, and it matches with that B. And character coming from that B is dollar, which indicates that we came to the beginning of the string, so we obtained the actual string using L to F mapping. We could easily observe the first, second, or third occurrences of A character or B or N characters. However, how can we achieve this easily when we have a large size string so that we have lots of rows? Uh, I will also illustrate it through banana example, but I will explain how we can do this. We can store a count table and use the following relation. The first column correspondence of last column index can be determined by adding counts of all lexicographically smaller characters plus occurrence of that character in the column. So I want to illustrate it. How can we obtain the count table? We can count the occurrences of A, B, and N. We can observe a single column and achieve the result. A occurs 3 times, dollar is 1 time as always, N takes place 2 times, and B takes place 1 time. Now we want to observe the first column correspondence of this N in the last column. How can we achieve this? We can firstly add the counts of all lexicographically smaller characters than N, which are dollar, A, and B. Count of dollar plus count of A plus count of B, and we would add the occurrence of that character in the column. What is the occurrence of that character in that column? It is 2. So we can add count dollar plus count A plus count B, which are 1, 3, 1, and occurrence of N in the third row, which is 2. So when we sum all of these, we obtain 7. So the seventh row is the first column correspondence of this N. Actually, we can also store an occurrence table to observe the occurrences of N. For example, N's occurrence in that row is 2, and we can store an occurrence table. However, it is mostly related with Ferragina-Mancini index and additional data structures used for pattern searching, which is out of scope. So I would not illustrate how to use occurrence table. I want to just illustrate how to use counts and occurrences in order to obtain the first column correspondence of a special character found in the last column. Why this L to F mapping is important? It is also used in pattern searching by using with FM index. And in this pattern searching problem, as I mentioned, some additional data structures are used, which are occurrence table and rank table. So we can search the patterns easily in a compressed manner. Thank you for listening. That's all I can say about Burrow-Wheeler transform. I hope you all enjoyed the video.